Okay, this video we are going to look at electrolytic cells. There's a little bit of stuff at the beginning on corrosion. Corrosion, a lot of you guys think of rusting when you think of corrosion, is technically a voltaic cell. Similar to the SDS stuff in the last video, you have the notes, you can read this. Usually on the diploma there would be at least one or two questions involving different things that we try to do to prevent corrosion. But similar to those other STS things, we're not really going to ask you any questions about it on your assessment pieces. So you can look at this and read it through. There isn't really too much in here that I would add to it that isn't in there. So you have those notes available to you on D2L. So just have a read through those on there. Okay, I am going to skip ahead all the way to slide number 7 to discuss electrolytic cells. So you've learned about voltaic cells by now, which are those spontaneous reactions. When we identify our SOA and our SRA, we find that it has the OA above the RA and it generates a positive E0. We don't have to do anything except connect everything and complete the circuit, and then those electrons spontaneously flow through the wire. An electrolytic cell is the opposite. What you find is in an electrolytic cell, these require an external source of electrical energy. So these are ones where we basically need a battery or a power source to run them. If we don't apply an electric current, nothing will happen. So electrolytic cells are all non-spontaneous reactions. In the first part of the unit, when we talked about non-spontaneous, we said nothing happens unless an electric current is applied. That's what we're doing in an electrolytic cell. We are applying an electric current, forcing that flow of electrons, and forcing a non-spontaneous process to occur. Okay, so this is called an electrolytic cell. Really important to make sure that you recognize that we kind of have three terms. So we have what we call an electrochemical cell. This is kind of like an umbrella term. An electrochemical cell just means it's some type of cell. These are then divided up, and they are divided up into your voltaic cells and your electrolytic cells. Okay, really important that you read carefully, because sometimes you guys just read electro cell and you assume that it says electrolytic, but sometimes it actually says electrochemical. So if it didn't specify what type of cell, really what you should be doing is find the SOA and the SRA. If you think about a voltaic, we said this was spontaneous. So that means my OA should be above my RA. Okay, but in the case of an electrolytic cell, we said it was non-spontaneous. So that means when I find my SOA, it's going to be down here, and my SRA is going to be up here. Okay, so if I'm unsure, the quickest way, list, because I'd have to do that regardless of what type of question I have, find the SOA and the SRA and see which combo are they falling under. Okay, so this little table here basically gives you some comparisons between a voltaic cell and an electrolytic cell. So a voltaic cell is a spontaneous reaction. Electrolytic cell is a non-spontaneous reaction. Other things that we find, right, if you think about a voltaic cell, we said that the E0 of that cell was a positive number. In a non-spontaneous reaction, the E0 of that cell is going to be a negative number. Okay, so in voltaic, we're converting chemical into electrical. In electrolytic, we're doing the opposite, and we're converting electrical into chemical. So a lot of the pieces are going to stay the same within our cells. Okay, we're still finding the SOA, we're still finding the SRA. We still have reduction happening at the cathode, oxidation happening at the anode. We still have electrons flowing from oxidation to reduction, so from the anode to the cathode. We still find that cations migrate to the cathode and anions migrate to the anode. So a lot of pieces stay the same, but there are a couple of pieces that are different. And one of those is the charge. Okay, you find that when we switch to electrolytic cells, the negative and positive switch around. Okay, So the cathode is now considered negative and the anode is now considered to be positive. And the reason for that is simply it's not a spontaneous flow of electrons. That electric current is pushing electrons to that one electrode and they build up there, building up that negative charge, which is why the cathode now gets a negative charge. So this table basically summarizes the differences between them, okay? Like I said, there are many things that are going to remain the same that we aren't actually going to change. Okay, there's one other thing that is different as well generally. Okay, and in a voltaic cell, that is that we must maintain separation, right? And so we did that either by having two separate containers or we did it by having that porous cup, right? We had some type of porous membrane or membrane that separated the two sides of our container. And we had to do that because it was spontaneous. And if we didn't have separation, the electrons would have just flowed automatically. But in the case of an electrolytic cell, it doesn't matter if the reactants are in contact or not because it's a non-spontaneous reaction. Nothing will happen. So you will find that in an electrolytic cell, it's often just one container. Okay, other difference, voltaic cell, we always had a voltmeter on the wire. Or sometimes if you look at some of the images from old diploma questions, you'll see there's maybe like a light bulb or there's something like that. In the case of an electrolytic cell, there's always going to be a power source or a battery, right? We need that flow of electrons to be coming from somewhere. So that's another piece that we're going to find different. So sometimes just from looking at the picture and determining if it's a voltmeter or a power source, we can sometimes immediately decide whether it's a voltaic cell or an electrolytic cell. All right, so normally if we were at school, we would now spend some time building a little demonstration for you of what this looks like. So we would be building an electrolytic cell using potassium iodide. So we would use a huge U-tube, so kind of like the ones we had for salt bridges, but just bigger. And we would have that. And then we would be filling it with solution, right? So we would have a solution line inside of here. And we would be placing some 1 molar, right? We're still always using 1 molar, so we would be placing some 1 molar potassium iodide inside of here. Okay, then what you would find is we would have to put some electrodes in, right? That doesn't change. We still need to have electrodes present. So we would stick 1 electrode over on this side, and the other electrode would go over here. Okay, and I'll see if I can find a video showing this one on YouTube, and if I can, I will pop that up on D2L for you to look at. So we're going to have 2 electrodes. In this case, they are going to be inert electrodes, and the reason they're going to be inert electrodes is if I have a solution of potassium iodide, I can't use iodine as an electrode because I2 solid, although it's a solid, it doesn't conduct electricity, right? It's not a metal. It's also generally more powderish. And then I definitely don't want to use potassium because potassium in water explodes. It is very flammable. If you've never seen it, you should go watch a YouTube video on people putting like potassium and sodium into water. It is rather impressive. Even if we were at school, unfortunately, I could not do that demo for you because they took all the sodium and potassium away from us a few years ago. So that means if I can't use potassium and I can't use iodide, I'm going to have to use an inert electrode. So let's just use some carbon rods. So say that that's carbon and that that's carbon. So we've got some graphite rods. Okay, then we are going to connect them using a wire. That doesn't change. So there's my wire. The difference though is that this wire would go to a battery. or a power source, okay? So instead of writing voltmeter on the line, we are going to represent a battery. And usually it will have a rectangle around it. Occasionally you will see that it will have like the, I want to say the physics way of drawing it, but for those of you that have taken physics 30 or in it, right, it'll have like, make that a straight line. It will have the little line and then the bigger line to represent that battery. Okay, so this would be our general setup. You'll notice that we don't have a salt bridge, and that's because we don't need a salt bridge because electrons are going to flow through the wire, and then we have ions inside of this salt bridge, not salt bridge, why am I saying salt bridge? YouTube, that are able to migrate around, right? So either we have flow going this way or we will have flow going that way, okay? At this point, it's kind of up to us what we want to make the anode and the cathode, right? If we had actually built this, we would probably be like, oh, well, this side is doing this, so we know what it is. But let's just make this side over here the anode and this side over here the cathode, okay? So from that, we know that the cathode is reduction and we know that the anode is oxidation. Okay, we also should be able to determine, sorry, the type of charges that we have. So when it was voltaic, the cathode was positive, but when we switch to electrolytic, those charges flip around. So the cathode is now going to be negative, and the anode is now going to be positive. So even though I still don't know what my half reactions are, I already know which way my electrons have to flow, right? They always flow from oxidation to reduction, or from that anode to that cathode. So they are going to flow this way. Okay, I also can decide which way each of these are going to flow, right? And that's because we still have the cation, which is the K plus, going to the cathode. And we still have the anion, which is the I minus, going to the anode. Okay, we still need to actually figure out what our reactions are and all of those other pieces of data. But we already can fill in a good chunk of this without actually getting to that point. So we're now going to do the same thing we did last time. We're going to list everything we have. So we have potassium ions. We have iodide ions. We have water. And I could list out the graphite rod, but I really don't have to. I already know that it has to be inert electrodes, so it's not participating in that reaction. You'll also find, if you check your data booklet, there is no carbon just in there, okay? So identifying what they are. So when I look at the potassium ion, it's all the way down at the bottom on the left-hand side. So it's an OA. I minus is maybe a third of the way down the page on the right-hand side. So it is an RA. And then water, we know, can either be an OA or an RA. So we need to decide between K plus and water, what is our SOA going to be? Okay, so we go to our data booklet, we start at the top on the OA side, we start scanning our way down. First one we hit is going to be the water, right? The K plus isn't until down here. So that means water is going to be my SOA. So there's my pen function here. Here we go. So water is going to be that SOA, right? So that means I know what half reaction is happening over here. It's going to be that water half reaction of 2H2O liquid plus 2 electrons turning into H2 gas plus 2OH minus. Okay, so a couple of things I would notice. As this cell runs, I would start to see that over here at this electrode, I'd start to get little bubbles being generated. And those bubbles would be because I'm generating that hydrogen gas, okay? I would also see, if I chose to add phenolphthalein, which a lot of times when we do this as a demo, we do, I would see that it turns pink over here. And that's because I have produced that hydroxide. Okay, other thing I do want to record while I kind of have my eye on this is what is the E naught for this half reaction. So the E naught for water is negative 0.0 0.83 volts, okay? So next thing I need to do is I need to find my SRA. So same deal, we go back to the data booklet. Now we're looking at the RA side, so we're starting at the bottom, we're working our way up. So there's K, but that's K solid. I have K plus AQ, so that's not what I'm looking for. Keep going, keep going. Here's an I minus, but it involves silver, which I don't have, so can't use that. Keep going. Oh, here's I minus. So that means I minus is going to be my SRA. So over here, because the RA is what undergoes oxidation, that's how I know that half reaction is happening here, I can write out that 2I minus AQ turning into I2 solid plus 2 electrons. Okay, so if we were doing this, you would see that what starts to be generated over here is a dark brown solution. And that's because iodine is dark brown. So you would see that it would start to kind of make the solution that would come and it would sink to the bottom. And that's because iodine doesn't really have a great solubility. It's somewhat soluble, but not really. So it's going to start to spread down, usually just the bottom. It's not going to start to climb back up this side. Okay, so sometimes when it comes to electrolytic, you guys get a little confused because you're like, oh, but as soon as I produce the products, then the spontaneous reaction could happen. But what you find is because this is open, that hydrogen gas has left. So there's no possibility for the reverse reaction to then happen. Okay, so usually we're still going to be able to maintain separation between those products, and that's what kind of ensures that we don't then get the opposite reaction happening. Okay, so we need to get the E naught for iodine. It is positive, sorry, I'm looking at my sheet sideways, 0.54. So overall reaction, I still need to generate one of those. So I'm going to look at 2 electrons, 2 electrons. I don't actually need to do anything to either of those. I just need to combine them. So we get 2I minus AQ plus 2 waters to give us an I2 solid plus an H2 gas plus 2 OH minus. Okay, we want to include the E naught for this cell. We calculate it the exact same way that we did previously. It is still going to be the cathode minus the anode. So we're going to get that negative 0.83 volts. And then we are going to subtract the anode. So we're going to subtract positive 0.54 volts. When we do that, let's see if I have a calculator handy, I do. So negative 0.83 minus positive 0.54, I get that this is equal to negative 1.37 volts. Okay, I should always find that an electrolytic cell gives me a negative E naught. So there's an additional thing that I need to include with this. So for me to actually make this cell run, I have to apply a voltage. We call that the minimum over voltage. Okay, minimum over voltage is how much voltage do I have to apply to actually make a cell run. So the minimum over voltage is always greater than the positive value of the E naught of the cell, right? Sometimes you guys are like, well, why can't I just put in exactly 1.37? But if I put in exactly 1.37, the net electrical difference is 0, so nothing happens, which is why it has to be greater than whatever the positive value is of that. Obviously, the more I crank it, the more voltage I apply, the faster this reaction is going to happen. But this would be the minimum that I would have to put to actually make this run. Okay, I would also want to talk about concentration changes and mass changes. So in these ones, these are a little messier because I have to discuss a whole bunch of things, right? I have to discuss the concentration of that potassium ion. Okay, the concentration of the potassium ion, because it was in my solution, is unchanged. And it's unchanged because it's not in this equation and it's not in this equation. Okay, I need to discuss the concentration of the iodide ion. Okay, in this case, that is a reactant over here. And we said that reactants get consumed, so it's going to decrease in concentration. Okay, in previous questions, we only talked about this and the mass of the electrodes, right? And I can still talk about the mass of those carbon electrodes. They are going to be unchanged because they are not participating in either reaction. But what's different is I have to talk about some other stuff because I produce some things that weren't originally in here. So I have to be able to indicate that I made those. So I need to talk about the mass of that iodine, right? Because we made iodine. So as we made that iodine, the mass of that will have increased, right? Then we need to talk about the concentration of hydrogen gas, right? We produce that hydrogen as this reaction occurred. So because we produced it, its concentration also went up. The last one to talk about is that hydroxide, right? Because we also produced that as our reaction occurred. And similarly, because it was a product, it will have gone up. Okay, so we need to make sure that we talk about how all those different things have changed. Okay, so looking at a couple of diploma questions, same as before, we'll just work through a couple of them. I will leave the rest of them for you to do. So here we have a cell. So in the electrochemical cell above, notice how it says electrochemical. It's not telling us specifically what kind. The calculated E0 cell value is blank. So what we need to do is look at the picture, right? The fact that this is a power supply should be telling me, oh my goodness, eventually I am going to stop coughing. It might be summertime, but eventually it's going to happen. Okay, so I have a power supply. The fact that there's a power supply is telling me that this has to be an electrolytic cell. Hopefully, I know by now that electrolytic cells have negative E0 values. So it's not A and it's not B. And the reaction is, if this is electrolytic, it is going to be non-spontaneous. So we would be looking at D. Okay. So the equation that represents the reaction that occurs at the cathode is, so in this question, we would want to list out everything we have. We would want to find the SOA, the SRA, and then from there, we know the cathode is reduction, so that SOA half reaction would be the one that we are picking. This is a molten cell, and we are going to talk a little bit more about molten cells, I want to say in the next video, okay? So here's a super common question. Every single diploma has some version of this, and you will see when you flip through the notes that you probably have about 5 different versions of this throughout it. So these are statements about electrochemical cells. There are 7 of them. It says the statements above that apply to both a voltaic and an electrolytic cell are numbered. So the net potential is positive. So that's saying the E0 of the cell is positive. That's only true in voltaic. That's not true in electrolytic. So that's not it. Number 2, the net potential is negative. That's only true in electrolytic, not in both. Reduction occurs at the cathode. Reduction always occurs at the cathode. So 3. Cations travel towards the cathode. Cations always migrate to the cathode. So 4. Electrons travel towards the cathode. We think about it, we've always said that electrons flow from oxidation to reduction. Reduction is the cathode, so 5 is true. Okay, 6, a flow of electrons is spontaneously generated. The fact that it says the word spontaneous should be telling you that that is not true, right? Because they're only spontaneously generated in a voltaic cell. And then the strongest oxidizing agent reacts at the cathode. That is true. So other versions of this question, sometimes it'll be the exact same list, but it'll say what's only true for a voltaic or what's only true for an electrolytic. But definitely there is the option of what is true for both. Okay, so here is a numeric response question. We'll work through this, and I think that'll probably be the last one that I do, and then I'll leave those other questions for you guys to kind of practice. So we have this electrochemical cell. It says match the number on the electrochemical cell above with the descriptors below. So increases in mass, movement of cations, movement of electrons, and site where oxidation occurs. So some of these are actually pretty quick answers. Some of them require a little more work. Why some of them are quick? The picture already tells us where the anode and the cathode are. So the movement of cations, we know that cations always move through the solution to the cathode. So that is going to be number 5. Okay, movement of electrons. Well, electrons always move through the wire, so it's either 1 or it's 2. But we've always said that they move from the site of oxidation, which is the anode, over to the site of reduction, which is the cathode. So that's going to be number 1. Okay, site where oxidation occurs. Well, oxidation either occurs at the anode or the cathode. So we're looking at 3 or 4. But hopefully by now you know oxidation always occurs at the anode. So we are looking at electrode number 3. So those I'm able to answer just by looking at the picture. The only one that I actually have to do a little bit of work to answer is the increase in mass, right? So if we think about what we have inside of this, right, we have solid copper, we have copper ions, we have sulfate ions, and we have water. So increase in mass, we basically find our SOA, our SRA, and then from there we see which one produces a solid, right? So let's go to our data book. So we're looking for Cu solid, Cu2+, SO4. So out of all of those things, our SOA is going to be the Cu2+. That produces Cu solid. So right away, the first one, we have just figured out what it's going to be. So Cu2+ plus 2 electrons becoming Cu solid. So if we think about what that half reaction is, right, and I'll just write it here really quickly. Again, I'm just not including those states because I'm just kind of, I don't want to say scribbling. I'm not scribbling, I'm typing, but you know what I mean. Okay, so that is the half reaction that is going to produce the solid. If we look at that as a half reaction, that is a reduction half reaction because our electrons are on the reactant side. Reduction always happens at the cathode. So the thing that is going to increase in mass is going to be the cathode, okay? So yeah, that is basically your electrolytic cells. Some pieces are similar to voltaic cells. Some pieces are definitely not. You have some stuff in your work booklet that you can be working on. You also have a few more diploma style questions in here that I didn't do as examples that you can work on solving as well.